All right, let's jump right in. The paper we're looking at today is Native Parallel Reasoner, Reasoning and Parallelism via Self-Distilled Reinforcement Learning.
Yeah, and this one is a big deal. The core takeaway here is all about building genuine intelligence with efficiency. NPR is a teacher-free framework.
Teacher-free.
Exactly. It lets large language models, LLMs, self-evolve true parallel reasoning. This isn't just some clever prompting trick. We're talking about changing the model's architecture to support, simultaneous thought.
And that change is built on three really key innovations. First, you've got this self-distilled progressive training paradigm. So no external supervision needed from a bigger, smarter model.
Right. And second, they introduce a new optimization algorithm called parallel-aware policy optimization. PAPO. It's designed specifically to learn when and how to branch out its reasoning.
And finally, the part that makes it all work in practice, the engineering. A robust NPR engine that keeps the whole thing stable during large-scale RL training.
And the results really speak for themselves. An NPR-trained Qwen 3.4b, which is a pretty small model, sees performance gains up to 24.5%, and it's up to 4.6 times faster than the old autoregressive baselines.
But here's the number that really stopped me.
That 100%.
The 100%. It demonstrates 100% genuine parallel execution on their test cases.
Yeah.
That proves the model has actually truly internalized the strategy. It's not a fluke.
Exactly.
That 100% figure is just. It's definitive. It tells you we've moved past this sort of pseudo-parallelism. So as LLMs move from just, being fluent with language to this deep, multi-step agentic reasoning.
Where they have to plan and execute and then check their own work.
Right. Relying on that old one-word-at-a-time sequential reasoning has become the major bottleneck. So let's unpack that. Why is sequential thinking fundamentally broken for complex problems?
It really boils down to two big things: architectural incompatibility and computational debt. Structurally, our current transformer engines and RL algorithms, they just weren't built for native branching and then bringing it all back together.
So if you want to explore 5 different ways to solve a math problem,
the engine is actively fighting you. And you also get that classic prefix trap. The model commits to plan A really early on, and then it realizes, way down the line that plan B or C was better. But by then, the cost of backtracking is just too high.
And what about the computational side of things, the inefficiency?
Well, older methods that tried to handcraft this, usually with independent sampling, they were hugely inefficient. Because each branch was sampled on its own, they couldn't share the key value states.
The KV cache.
Right, the KV cache from the prompt or from the shared parts of the reasoning.
So wait, if you have a complex prompt that's, say, 5,000 tokens long, and the model wants to explore 3 branches, it has to recalculate those 5,000 tokens 3 separate times.
Precisely. That redundancy creates this prohibitive linear latency cost, O of n. It just makes it totally impractical for any real-time use case. You're just trading one kind of bottleneck for another.
Which brings us to what the paper calls the intelligence ceiling. I found this to be a really insightful critique of a lot of the previous work.
It's the third critical problem, and it's tied to supervised learning. You have frameworks like Multiverse, which did get native parallelism working, but they leaned really heavily on data distilled from stronger, often proprietary teacher models.
So the student model is just learning to copy the teacher.
Yes, and that's the ceiling. If the teacher model reasons sequentially, then the student is just learning to mimic that sequential path, even if you force it into a parallel format.
It's like you're putting a sequential thought process into a parallel box.
You got it. It prevents the model from ever discovering truly novel, intrinsically parallel strategies, the kind of strategies a teacher model built for left-to-right generation would never have come up with on its own. NPR smashes that ceiling because it's entirely teacher-free.
And this is where it gets really interesting. They use this structured 3-stage progressive curriculum. So the model goes from mimicking the format to internalizing the structure to finally, optimizing the policy. That sounds like a very stable way to bake in such a big change.
Oh, it's critical for stability. You can't just jump straight to the RL part. The model has to learn the language of parallelism first.
So walk us through stage 1, NPR 0, the format discovery part. How do you train a model to just spontaneously output a parallel structure when it has no parallel data to learn from?
They define a really clear map process reduce schema, and they use specific structured tags to enforce it. Guideline for the overall map, plan for the individual strategies, step for the actual parallel work, and takeaway to bring it all together.
So the goal at first is purely to get the syntax right.
Exactly. They use a standard RL algorithm, DAPO, but with a very specific reward function. The format check is the gatekeeper. If the output passes the structural check, it gets a baseline reward of 0, but if it fails,
It's penalized.
heavily, up to a -2 penalty. Only if the format is correct does the accuracy reward even kick in, +1 for a right answer, -1 for a wrong one.
That strong penalty basically forces the model to learn the non-negotiable grammar of parallelism first.
Right. And this whole process generates NPR 0, which is a model that can generate these structured trajectories. It's producing simulated parallelism. It knows how to write it, but it doesn't have the architecture yet to actually run it efficiently.
Okay, so stage 1 taught it the format. But like you said, format isn't architecture. So how do they get this new language into the model's core engine? This must be stage 2, NPR beta.
This is that crucial bridge. It combines self-distillation with supervised fine-tuning, SFT. They take all the outputs from NPR 0 and use rejection sampling.
So they're filtering for the best examples.
The very best. They only keep the trajectories that are both correct and have perfect parallel structure. This creates a high-quality, self-distilled dataset they call DALAFET, and it's demonstrably better than data you'd get from a sequential teacher.
So the model is effectively writing its own specialized textbook on parallel thinking.
Precisely. Then they fine-tune on this new data, but, and this is key, they introduce strict topological constraints. This is where the structural integrity gets baked in. There are 2 main mechanisms for this.
The first one being the parallel attention mask.
Yes, the mask is essential. For any tokens inside those parallel step blocks, the mask explicitly isolates them from each other. Functionally, it's like putting up privacy screens between the parallel tasks.
So one task literally cannot see what the other's doing.
It can't. Not until they're all synthesized in the final takeaway block. It forces genuine independence and prevents any, information leakage between the branches.
That's critical. You want it to solve subproblems independently, not just peek at what the other branch is doing.
And the second mechanism is the parallel positional encoding. This basically resets and aligns the position IDs for each parallel branch. It's a very clever trick because it lets the engine efficiently reuse the KV cache for all the shared context that came before the split.
So that's how they get around that computational debt problem we talked about. No more recalculating the whole prompt. That's what unlocks that 4.6x speedup later on.
That's a huge part of it.
Okay, so NPR beta now has the right format, and it has the native architectural support. So what does this all mean? We shift from this structured imitation to true adaptive exploration, stage 3.
Stage 3 is native parallel RL. And this uses their novel algorithm, Parallel-Aware Policy Optimization, or PPO. The model they start with, NPR beta, already understands the structure, which helps a ton with stability.
And the key challenge here, as you mentioned, is that RL fine-tuning can sometimes make the model forget.
Exactly. It's catastrophic structural forgetting. Standard algorithms like PPO, they have these safety mechanisms that clip gradients, and they often click the gradients on special tokens, like our step and takeaway tags, because those control structure, not content.
And if you clip the gradients for the very tokens that define the parallel structure,
the model just unlearns the whole format. It worked so hard to get in stage 2. The structure just dissolves.
Wait, but isn't removing that clipping mechanism dangerous?
Yeah.
If you let those critical tokens get hit with huge, noisy gradients, you could risk the whole policy just diverging.
That's the trade-off, and that's why PAPO is so clever. The solution is to preserve the gradients on those special tokens, so you remove the clip masking, but to keep it stable, you get rid of importance sampling entirely. They adopt a strict on-policy objective.
So instead of estimating the value of a rollout using data from a slightly older policy, which is what importance sampling does, they are sticking only to paths generated by the current live policy.
That's right. They use the stop gradient function on the old policy's probability and the loss function. You can see it in equation 6. This maintains stability while making sure those critical structure-defining tokens are always being optimized correctly.
That is a very elegant way to sidestep the instability. And you mentioned a change in normalization, too.
Yeah, because they're constantly filtering out structurally invalid samples during rollout, the variance at the group level just collapses. So they switch to batch-level advantage normalization, sort of light PPO style. The advantage is normalized across the entire batch, not just a small group, which keeps the variance healthy and stops the model from overfitting.
Okay, that covers the algorithm. Now let's talk about the engineering, the NPR engine. This sounds like the crucial infrastructure work that keeps the whole thing from just falling over when you try to run these deep parallel rollouts at scale.
It was absolutely crucial. It involved a lot of refactoring of SGLang to get back to deterministic, stable behavior. For example, a huge issue was the KV cache double free bug.
The memory leak problem, making sure one process doesn't accidentally erase instructions that another process is still using.
Precisely. Under heavy branching, the shared KV paths were being recycled way too aggressively. It was leading to context corruption, memory leaks. The fix was to replace that with an explicit, budget-aware reclamation strategy. They just flush the cache and reallocate when usage gets close to a set budget. Stops corruption cold.
Good engineering. But what else broke when they put it under the stress of parallel RL?
The global token budget. The original engine only tracked the length of the longest single branch, but parallel decoding multiplies token use by the number of active branches.
So the RL process could just crash mid-rollout because the system thought it had enough token budget when it really didn't.
Correct. So they fixed that by making the length accounting branch aware. It now tracks the total active branching factor. They also had to deal with structure violations. They put in this lightweight pre-branch format validator. It's like a tiny bouncer that checks the structure before any expansion happens, preventing illegal schemas from ever wasting compute.
That's smart. A small, cheap check to prevent a big, expensive failure.
It's exactly that. And one final, small but necessary fix. They applied a mild repetition penalty, just 1.02, but only inside the step contexts. This just keeps the reasoning traces concise and stops the model from repeating itself during the core computation.
So after all that heavy lifting on both the algorithm and the infrastructure, let's look at the payoff. The results are really significant, especially because they did this on a smaller model, Twin 3.4b.
The performance improvements really validate every single step of the framework. Let's start with the self-distillation. Just replacing the old sequentially distilled data with their self-distilled data, NPR beta, led to an average gain of almost 9 points across the board. The zebra logic task jumped from 60% to over 76%.
Wow.
Yeah. It confirms that having the model generate its own natively parallel data is just fundamentally better than having it imitate a sequential teacher.
And then the final RL stage gives another consistent boost on top of that.
Absolutely. The final NPRL stage consistently beat the sequential RL baselines. On AME24, accuracy went from about 57% with sequential RL up to 63.3%. That's a huge 6.2-point gain. It really proves that PAPO and the stable engine are enabling powerful structural exploration.
And let's talk about that 4.6x acceleration. Inference speed is everything for deployment.
The speedup comes from executing those step tokens at the same time, while also getting that massive shared context reuse from the new engine. But what's really interesting is that the speedup scales with difficulty. You see a 4.6x speedup on a really hard math task, but only 2.9x on an easier one.
Which means the advantage of parallelism grows exactly when you need it most, when the problem is harder and requires more search.
Exactly. And that brings us back to that 100% metric, the parallel reasoning trigger rate. It's the definitive proof that the model now thinks in parallel.
It's structural integrity made visible.
It is. A baseline model like MV32B was all over the place. Sometimes it would only trigger parallelism 45% of the time. But NPR Inst achieved a uniform 100% trigger rate across all 8 benchmarks they tested. The strategy is no longer optional or fragile. It is fully baked in as the model's default way of solving hard problems.
And that's the truly groundbreaking part for me. It's a qualitative shift in how the model thinks. It's not just faster, it's approaching problems differently. How does that show up in practice?
The case studies are fascinating. They show NPR adapting the style of parallelism to the problem. For a complex math problem, it uses parallelism for decomposition. It breaks the problem into 3 subproblems, solves them in parallel, and then, this is critical, it uses the takeaway block for a reflective cross-checking process to synthesize the results.
So it's decomposition followed by a self-verification step.
Exactly, but contrast that with a logical or geometric problem, like angle chasing. Here, it uses parallelism to explore multiple independent solution strategies simultaneously.
What do you mean?
It might run Plan 1 using a formula, Plan 2 using some properties of cyclic quadrilaterals, and Plan 3 using a known geometric theorem, all at the same time.
It's essentially creating an internal multi-agent verification system on the fly. By exploring these diverse independent paths and then checking for consistency at the end, the solution becomes inherently more robust.
It fundamentally increases reliability. If 3 completely different lines of reasoning all point to the same answer, your confidence in that answer is way higher. And that capability, this reliable, adaptive, internal cross-checking, that's the hallmark of true agentic intelligence.
So what does this all mean, wrapping up? We've seen a clear, reproducible path to building genuine parallel reasoning from the ground up. It doesn't need giant teacher models, which is huge. The results on a smaller model like Qwen 3.4b confirm this is effective even for more resource-constrained systems.
It establishes parallel reasoning as a reusable cognitive primitive. It's not a trick anymore. This work shows that focusing on specialized RL, like PAPO, and robust engineering, like the NPR Engine, is the key to getting reliable, efficient, and structurally sound AI behavior. You're teaching the policy to use the hardware the way it was meant to be used.
It's a complete architectural evolution. So I'll leave you, the listener, with this thought. If smaller models can be trained to reliably generate these diverse, self-verified parallel plans, achieving major speedups and 100% structural fidelity, how quickly will this type of natively parallel architecture become the default industry standard for all complex multi-step agentic AI systems?